Defining the derivative. Now that we have both a conceptual understanding of a limit and the practical ability to compute limits, we've established the foundation for our study of calculus, the branch of mathematics in which we compute derivatives and integrals. We've previously learned that if you want to find the rate of change of a function at a specific value a, that we would find the slope of the tangent line there. That's actually finding the derivative, so let's formally define this. The derivative of a function f at a number a, notated, so the notation we use for derivative is this f prime of a, represents the slope of the tangent line for the function of f at a, and it's defined as follows. The limit as x approaches a of f of x minus f of a all over x minus a. And you may recall this formula that we used back when we were finding derivatives or the slopes of tangents, which is when we called them there, the longer way. So that's provided this limit exists. We can also use this formula. So recall when we were doing this, we started looking at values where this second point, or that we're using to find that slope of the tangent, was getting closer and closer and closer to a. And so said that we defined that as a plus h. So h was how far away we were from that initial value. So we can formally define that by saying the limit as h approaches 0 of f of a plus h minus f of a all over h. And the reason it's over h is because normally it would be over the x value. So we'd have, let's do this to the side, a plus h minus a. So this x value minus this x value would be in the denominator. Well, those cancel out, and that's why we're just left with that h in the denominator. Okay, let's actually put these formulas in action. Find an equation of the tangent line to the graph of f of x equals x squared at the point 3, 9. So we've done this before. If you recall the beginning of this course, we learned how to find the slope of a tangent line by either looking at it graphically and estimating what that tangent line would be, finding the slope of it, or numerically using a table of values and seeing what happens as our x values get closer and closer to 3 and what's happening to the slope. Those can be kind of tedious, and they're also not accurate because we're estimating. So now that we've learned limit laws, and now that we've just gotten this formal definition of the slope of a tangent, which is the derivative, now we can find out exactly what it's going to be. So this is our x, here's our y. All right, so I'm trying to find the derivative, the slope of the tangent. To find the equation of it, I first need to find the slope. So to find that slope of the tangent line, that's finding the derivative of it. And we're finding it when our x value is 3. Okay, so let's use that first formula so you can see how that one comes into action. So this would be finding the limit as x approaches a, which is 3, of f of x minus f of a all over x minus a. So we can replace those a's with that 3. Okay. So now this becomes the limit as x approaches 3 of f of x, which is x squared, minus f of 3. So f of 3, when your x value is 3, your y value is 9. You could also plug in 3 for x or substitute in 3 for x and get 3 squared, which is 9, all over x minus 3. So now we can use those limit laws that we've learned to evaluate this limit. Right now, if I substituted in 3 for x, I'm going to get 0 over 0, which is an indeterminate form. So I can't quite substitute that in yet. So let's see if we can use that problem-solving strategy we've learned previously to get this function into a form that I can evaluate. So I can factor that numerator as x minus 3 times x plus 3. Denominator is x minus 3. Those are going to cancel. And now I'm left with the limit as x approaches 3 of x plus 3. So now at this point I can actually just substitute that 3 in, and I'll get 3 plus 3, which is 6. So the slope of the tangent at the x value of 3 is 6. Once we have that, we can go back and actually find the equation of this tangent line. So remember we learned y minus y1 equals m times x minus x1 for finding the equation of a line. So this becomes y minus 9, which is that value, the point that we've got, equals the slope times x minus 3. So y minus 9 equals 6x minus 18. Y equals 6x minus 9. Let's actually confirm this by looking at this graphically. So we can see here, here's the graph in orange of f of x equals x squared, and here is the line y equals 6x minus 9, and you can see right here at 3, looks like that is definitely about that equation line, or the tangent line through that point. Okay, so let's look at another example of this. For f of x equals x squared minus 4, find the derivative of f at 1. Then find the equation of the tangent line at that point. Okay, so to find the derivative of the function at 1, let's actually use both equations for finding the derivative, just so you can see that both will result in the same answer. So we'll start with the x approaches a formula. So this, in this situation, our a is 1. So the limit as x approaches 1 of f of x minus f of a, which is 1, all over x minus 1. So that's going to give us the limit as x approaches 1 of f of x, which is x squared minus 4, minus f of 1. So f of 1 is going to be x squared, so 1 squared minus 4. I'll do that up here. So that's going to be 1 squared minus 4, which gives us negative 3. So minus a negative 3. And then that's all over x minus 1. So this becomes the limit as x approaches 1 of x squared minus 1 all over x minus 1, because that becomes a negative 4 minus a negative 3 is the same thing as negative 4 plus 3, which is negative 1. And then that will, so right now if I go and actually try to substitute 1 in for x, I'm going to get 0 over 0, so I am in that indeterminate form. So right now I can't just substitute that in. So let's use some of those problem-solving strategies we learned in earlier sections to find an equivalent function. So I can factor x squared minus 1 as x minus 1 times x plus 1, and again that's all over x minus 1. So those two pieces will cancel, and I'm left with the limit as x approaches 1 of x plus 1. And now I have a polynomial so I can actually substitute 1 in now for x to evaluate this limit. So I get that the limit is 2. So the derivative of the function at 1 is 2. Let's go through and use the other formula for this. So the other formula states to find that derivative, I'm actually going to do this in green, not in red. So to find that derivative, it's the limit as h approaches 0 of f of a, which is 1, plus h minus f of a all over h. Okay, so right now if I tried to substitute 0 in for h, we can't do anything. So let's go through and figure out, evaluate what f of 1 plus h is. So f of 1 plus h means I'm going to go to my function, and anywhere I see an x, I'm going to replace it with a 1 plus h. Okay, now remember that 1 plus h squared is the same thing as 1 plus h times 1 plus h. We can't just distribute that squared through. We need to actually FOIL this whole thing out. So that's going to give us 1 plus 2h plus h squared minus 4. All right, so now let's plug all of that in. So the limit as h approaches 0, so again I just found that f of 1 plus h is this, so that's what I'm going to substitute in. So I get 1 plus 2h plus h squared minus 4, and then I still have to subtract f of 1, and we found f of 1 was negative 3, so minus a negative 3 all over h. Okay, still cannot substitute in 0 for h yet because I'm going to have that 0 in the denominator, which is an indeterminate form. So let's continue going and see if hopefully we can simplify this up. So minus a negative 3 becomes plus 3. And then I can simplify that up a little bit more. So if I do 1 minus 4 is -3, plus 3 is 0. So those end up all canceling each other out, and we're left with 2h plus h squared in the numerator over h in the denominator. Now this is great because I can actually factor an h out of that numerator. And the reason that that's helpful is that now these h's are going to cancel, and I'm left with the limit as h approaches 0 of 2 plus h. So now I can actually substitute 0 in for h and evaluate that limit, and I get 2 plus 0, which is 2. So you can see here we found the exact same formula for the slope. So now if we were trying to find the equation of that tangent line, okay, well we need a point and a slope so that we can use this point slope formula. So we know that that slope is 2, but I need to see if I have a point. So we were trying to evaluate this at x equals 1. So when x equals 1, that y value we found, the output was -3. So there's the point that I'll be using because that's the point on that equation that this tangent is going to touch. So this becomes y minus a -3 and then minus 1 here. So I get y plus 3 equals 2 times x minus 1. So y plus 3 equals 2x minus 2. Y equals 2x minus 5. So the equation of the tangent line at x equals 1 is y equals 2x minus 5.